Hello and welcome to yet another video of Cornerstones of Math. Let me explain today's problem. First, consider a sphere x squared plus y squared plus z squared equals 1 in 3D coordinate space. Then consider cutting this unit sphere by two planes that are perpendicular to x-axis and apart from each other by distance 1. So this interplanar distance is 1. And you can also notice that the intersection between two planes and a sphere consists of two circles whose sizes change depending on the position of the planes. We can mathematically analyze this situation by identifying the changing variable, which in this case is this x. Here, x is the distance from the origin to the plane that is on the positive x side. Under this definition, you can easily notice that x changes from 0 to 1. If we change the value of x between 0 and 1 and indicate two planes and intersecting circles accordingly, it will look like this. As you can see, moving planes, changing circles, changing sizes of the circles. But aside from just circles, we can think of many other changing things in this setting. And let's actually start from one-dimensional quantity and move on to higher dimensions. We can think about the circumferences of two circles that are intersections between two planes and a sphere. If we denote these circumferences as C1 and C2, we can think of the combined circumference C1 plus C2. And moving on to two-dimensional quantities, we can think of the areas of these two circles. For the areas of the cross-sectional circles, let us call them A1 and A2. And let's think about the combined area A1 plus A2. And before we move on to 3D, there is actually one more type of areas we can think of. You see, by placing two planes like this, the sphere is divided into three parts, and on both ends we have these two surfaces which shaped like a cap. And we can think of the surface areas of these two cap-shaped surfaces. Let's call these surface areas S1 and S2 in order to distinguish them from the areas of the circles A1 and A2. And finally, moving on to 3D, let us think about the volumes of these two regions enclosed by cap-shaped surfaces and two planes. Then we can think of the sum of two volumes V1 plus V2. So we can think of these four quantities from the given circumstance, and our main problem is like this. When do these values become maximum or minimum? That is, at what value of this x, which changes from 0 to 1, do these four quantities become maximum or minimum? I am going to tackle this problem, and actually I am going to tackle the problem in this order, because I just think that the math becomes more advanced and more involved in this order, and for no other particular reasons. So let's first take a look at the area of two circles A1 plus A2. In order to calculate the area, we need to find these two radii, R1 and R2. Then we can calculate the area as A1 plus A2 equals pi times R1 squared plus R2 squared. And here's the thing. The sphere in the problem can be generated by first constructing the circle x squared plus y squared equals 1 on the xy plane, and then revolving that circle about the x-axis. And in order to avoid advanced math concept whenever we can, and to keep figures as simple as possible, let's think about the problem on two-dimensional xy plane. On the xy plane, two planes cut the circle like this, where this length is the changing variable x, and these are two radii R1 and R2. So from bigger illustration here, if this length is x, then this length must be 1 minus x, or you can say that this coordinate is x and this coordinate is x minus 1, which is now negative. It doesn't really matter here. From the equation of the circle, y squared equals 1 minus x squared. So we know that R1 squared is given as 1 minus x squared and R2 squared is given as 1 minus x minus 1 squared. Therefore, area A1 plus A2 is given as this. Now this may confuse you due to many parentheses, but this is essentially a quadratic function which we can easily handle. Basically, We expand everything and simplify. Then we can easily complete the square to convert it into a vertex form. So we have a1 plus a2 given as pi times minus 2 times x minus 1 over 2 squared plus 3 over 2. This is a quadratic function that is maximum at x equals 1 over 2 and minimum at the two endpoint x equals 0 and 1. That is, maximum in the middle and minimum at both ends. Next, we move on to the sum of circumferences of two circles, C1 plus C2. This is quite similar to the previous case, except now we have 2 pi r instead of pi r squared. And we have already calculated radii r1 and r2 in the area case, this time with square roots, because the formula requires r1 and r2 instead of their squares. So we have this, which equals 2 pi times square root of 1 minus x squared plus square root of 2x minus x squared. So now it is tricky to find its maximum and minimum points, because now we have to use the derivative to do so. So by taking derivative, you can easily find out that the derivative is given like this. So we let this derivative equal 0 in order to find the extremum points, which means that this equation holds. So multiplying like this, we have this, and in order to remove radicals, we have to square both sides, which gives this, which leads to this equation, and notice that terms cancel out, which gives this, and eventually x equals 1 over 2. This is the value that makes derivative 0. And although it is not straightforward to track the sign of the derivative, we can just compare the values at x equals 1 over 2 and at two endpoints 0 and 1 to find out that c1 plus c2 is maximum at x equals 1 over 2 and minimum at x equals 0 and 1. So again, just like the areas, maximum in the middle and minimum at both ends. And now let's actually move on to the volumes. So we have to find the volumes of these two solids, which are both solids of revolution just like the sphere. Using XY plane diagram, they can be obtained by revolving these two shaded regions about the x-axis. And as for their volumes, there's this neat formula. The volume of the solid of revolution formed by revolving the area under the graph of y equals fx from x equals a to x equals b about the x-axis is given as pi times integral from a to b fx squared dx, or in a more simpler notation, sometimes it is just written as pi times integral y squared dx. Now many of you might already know how this formula is derived, but I will just briefly mention here since we have to do the similar thing in the next part. Simplifying a lot, the volume is essentially the sum of the many infinitesimal volumes dv, and when we are dealing with the sum of infinitesimally small things, we use integral notation. In this case, dv is the volume of a cylinder or a disk located at position x having infinitesimally small thickness dx. Then the volume of the cylinder is, its base is a circle, so the base area is pi times the radius squared, where the radius is fx. And the height of the cylinder is dx, so we have dv equals pi fx squared dx. And that's why the formula looks like this. So let's apply this to our case. In our case, from the equation of the circle, y squared is given as 1 minus x squared, so we have pi times the integral of 1 minus x squared, where the interval of integral is first from minus 1 to x minus 1, and then from x to 1. Here, the antiderivatives are the same, x minus x cubed over 3, and although the result seems quite dirty, you can easily notice that x cubed terms eventually cancel out, making this another quadratic function. So with this quadratic function, we can easily convert it into a vertex form, And because now the leading coefficient is positive, this is the quadratic function having minimum value at x equals 1 over 2 and maximum at two endpoints 0 and 1. So now we have the opposite trend compared to previous two cases. And now the final one, the surface area of these two surfaces, which are parts of the sphere. But how can we calculate their areas? Well, let's remind us that from volume calculation, we have obtained the solid of revolution by revolving a region under the curve about the x-axis. This case is no different from that, since the surface of our concern is also a surface obtained by revolution. That is, we take these two arcs, which are parts of the circle. If we revolve these arcs about the x-axis, we obtain the surfaces. So the question is, what is the formula for this? I mean, is there a formula for the area of the surface of revolution formed by revolving the graph y equals fx about the x-axis from x equals a to x equals b? Well, just like the volume calculation, first we need to find the infinitesimal surface area ds for infinitesimal height dx at arbitrary position x. And this time it's not a cylinder, but rather a lateral surface of a truncated cone. So we need to find this lateral surface area, and here's the thing. The lateral surface area of a truncated cone with bottom and top radii of r1 and r2 respectively, and the slant height s is given as pi times r1 plus r2 times s. Now don't ask me to derive this formula, I'm not gonna do it, it's just simple geometry, and I am only gonna use it. So applying this formula, ds is given as pi times the sum of two radii, f of x plus dx times dl, which is this slant height of our truncated cone. Here, dl is expressed like this by the Pythagorean theorem, and this f of x plus dx minus f of x part can be approximated to derivative f prime x times dx, given that the derivative exists. So we obtain this. Therefore, we eventually obtain this result for ds, which eventually leads to the formula s equals 2 pi times integral from a to b of fx times square root of 1 plus f prime x squared dx. This is the formula for the area of the surface of revolution, and now it's time to apply this to our problem. So here's the formula, and from our equation of the circle, we have this expression for y, the upper part of the circle, which gives this derivative. So we have everything we need, and if we calculate this part first, which is y times square root of 1 plus derivative y prime squared, we have this, and simplifying this part, it simplifies to this, so we have simply 1. So this entire part is 1, so the surface area S1 plus S2 becomes just the integrals of 1 from minus 1 to x minus 1, and then from x to 1. So carrying out this rather simple integral, we obtain 2 pi. That is, the surface area is constant. It does not depend on x and always gives the same value, the half of the surface area of the sphere. This is one of the interesting properties of the sphere. If the length of the interval of revolution remains unchanged, the resultant surface area remains unchanged. And that's all for today's video. Thank you all for watching, and please don't forget to hit that like and subscribe buttons, and I will see you in another video.